Let me begin with the story, and let me begin with the moduli space mg and bar of stable and pointed curves. So what do we know about this space? We know that first of all the points of the space correspond to curves so C is a curve of arithmetic genus G, and plus n points which are numbered. So PI's are non-singular points which satisfy several conditions, and one of them is a condition on singularities, and the other one is a numerical condition. Or some people call it the stability condition. And for the condition on singularities, let me write it this way. One requires that C is reduced, that PI are, maybe I'll repeat it here, are non-singular points. So PI C is nodal at worst, so it may have singularities, but locally there are just ordinary nodes, so given by an equation just xy equals 0, and so PI are not the nodes. The curve also has to be connected and projective. And then for every given G and N, there exists this, there exists two objects. There exists the moduli stack, which is smooth, Dilley-Mumford stack of dimension 3G minus 3 plus N. And there exists this MGN bar, its coarse moduli space. And this is a projective algebraic variety with quotient singularities. So the difference between this moduli stack and the coarse moduli space is lies in the automorphisms of such curves. And the stability condition precisely say the way it's normally stated or very frequently stated, it's stated that in the way that the group of automorphisms of this pair, P1, Pn, has to be finite. And the way I prefer to state it here is this way. So I prefer to state it in this form. So I require that the canonical class of C plus sum of PIs, so this divisor is ample. So let me remind what this means. So if we have a curve and we have a component, so this is the curve C, and if there is a component E whose arithmetical genus is at least 2, then the automorphism group of this component is already finite. And if the arithmetic genus is 1, then its E is either elliptic or, since it's nodal, it could also be rational with one node. So it may look like this. And in both cases, the automorphism group is one-dimensional. So in the first case, it would be E itself extended by some finite group. And in the second case, it would be this nodal curve contains a copy of the multiplicative group. So working over C, let me just write C star. And again, extended by a finite group. There is a reflection, for example. And so to make this, for this stability condition, to make the automorphism group finite, one needs to fix one more point. So if this curve is elliptic, for example, and it has one point of intersection with the rest, then with the rest of the curve, then instead of looking at the automorphism group of E, we look at the automorphism group of E plus that point, and that's already finite. And the same way here. So in the case when the arithmetic genus of E is 1, the requirement is that there has to be at least one special point. And special means either one of these points Pi should be in E, or either one of these points should be here, or E must intersect the rest of the curve. So this is, if you formulate it in this form, now if you look at the canonical class of E, then since C is nodal, then it has a dualizing sheaf, and this is an invertible sheaf. Dualizing sheaf. And it has a degree, and the degree of this sheaf when we restrict it to E is given by this formula. Plus the number of points here in the intersection. And so when we have these non-singular points, this is still a non-singular, this is still an invertible sheaf, so it has a degree. And so I just copy this number plus the number of points of pi in E. And to say that it's positive, in this case, in the case of arithmetic genus 1, means what does it mean? Well, this term will be 0. And so it means precisely that either there is, well, it means that there is at least one special point, which is either of this form and will be counted here, or of this form and will be counted here. Now, finally, when the arithmetic genus of E is 0, the curve is then P1, and the automorphism group of P1 is PGL2, and so it's three-dimensional. And to make the automorphism group finite, one needs at least 3 special points. And if you look at this formula again, then this number becomes -2. And to make this number positive, well, the answer is the same. One needs 3 special points, which are either here or here, and count it equally. So this is the most basic moduli space in algebraic geometry, which is nonlinear, which is not about sheaves, but about geometric objects, is about varieties. And most of us know that it has many applications in arithmetics and geometry and topology and physics, etc., etc. And one of the most important, or at least one of the most productive, is the Gromov-Witten invariants. Now, around, well, 1989, well, it doesn't have to be around. So in 1989, precisely, Kohler and Shepard-Barn published a paper where they made the first steps for extending this construction to the higher dimensions. So the aim, so this is just the general direction, the aim was to try and extend this construction to higher dimensions and begin construction of moduli spaces of stable surfaces instead of curves. And once you begin on this road, then you realize that you shouldn't stick with surfaces, but should look at higher dimensional varieties. And you should not look just at the varieties, but add something like a point. So consider pairs x, b1, bn, etc. So this was just the beginning. So the story only started in that year. So let me give you a few highlights on this way, on this path, and I will call this the theoretical track. So maybe the most important idea in this field appeared in this paper, and I will review it for you a little later. But to actually construct the space, well, here are some highlights on this theoretical track. In '96, I proved the boundedness of stable surfaces with fixed kx plus b squared. And so to construct this moduli space, one of the first questions you should answer is if you fix some basic invariants, do you even have a bounded family?
Sorry, k plus b will be ample.
Right, where this kx plus b will be ample. So kx squared for stable surfaces, which I will later replace by kx plus b when considering the pairs. So for curves, the question is really trivial. If the degree of this kx plus b, which is my shortcut for the degree of this invertible sheaf, is 2g minus 2 plus n. And so to begin with, if you fix this degree, then there are only finitely many values for g and n, obviously. And once you fix g and n, there are only finitely many combinatorial types of such curves that one construct. And so obviously one is dealing with the bounded family. And one can even say what the dimension of the modulus of the total moduli space will be. And for surfaces, well, I haven't said anything about surfaces, but as you will see later, the question is much more complicated. And even if you fix this numerical invariant and as many more as you like, reasonable numerical invariants, it's still very, very non-obvious that you are dealing with the bounded family. For example, that the singularities that appear on such surfaces are bounded in some way, belong to a finite list, or maybe finite list of families. Well, so that is still a theoretical track. I mean, this is a theorem which allows you to make some corollaries, but later on with Mori, so there is a paper with Shigefumi Mori where we made some of these estimates explicit, but they are very unreasonably explicit. There are. Let me just give you one. Just to illustrate. So one corollary of this theorem is this. So suppose you have a family, a degenerating family, xt to x0. And you begin with the family of surfaces which are extremely nice, which are smooth, projective. They have ample canonical class. And you degenerate. And in the limit, you get some of these stable surfaces that I'm going to talk about. And it's somehow, so I don't specify right now what it is, but somehow it's a higher dimensional version of a stable curve. So it's singular, maybe has several components, maybe it's nodal in codimension 1. And a basic question you would like to ask is, well, how many reducible components this surface may have? And if you ask this question for curves, then the answer is immediate. So when we started with this degree, and it had this, there was this simple formula for the degree. And then when we degenerated, if the curve C has components Ej, then the degree of omega x of B will be sum of these degrees over the reducible components. And on each component, the formula, well, so this is my omega x of B. The degree is given by this formula, and this number should be, first of all, it should be positive, and second of all, it should be an integer. And this implies that it should be at least 1. Which means that the number of these Ej's is at most 2G minus 2 plus n. And so you have a very easy bound on the number of the irreducible components. And if you started with something without points, then 2G minus 2 would be your bound. So if you try to ask the same question for surfaces, then the answer is, so what this theory implies is that the number of irreducible components is less or equal than something like 10 to the 20 times kx squared. And so that's not a very good bound. And other people improved on this, and in the case at least when there is no boundary, so when it's just a surface, when the situation is like this, I think this is the known bound, so something like 1440 times kx squared. And so if you start with the surface of square 1, a very nice smooth projective surface, all this theory tells you is that, well, the degeneration maybe has that many irreducible components. And then so when you look at this, you decide this is really theoretical. This is maybe not very useful for computations. So let me continue with this theoretical track anyway. And so the 2000s were the period of clarification of the moduli problem. And so a number of papers by Hassett and Kovac and by Hacking and more by Hassett and more bipolar recently. And so even though the main idea, which is still to come for these moduli spaces, is already apparent in this first paper, the fact that the surfaces are singular requires one to be very careful and specify precisely what the families considered are. And there is a number of very delicate technical problems that had to be dealt with. And so that required all those papers. And so one important paper, recent paper by Kohler, is called Husks and Hulse. Now, around 2006, a book writing project commenced, led by Kohler. And maybe 3 years later, it started in earnest, let me put it this way. And so now, thanks mostly to efforts by Janos, there are several chapters, and so he seems to be very serious about it. And so the good news is that when Kohler starts something, that is likely to be finished. And so hopefully this will appear sometime soon.
So what is the status now of the technical problems? Have they considered
solved? And the status is as follows. For dimension 2, and if you work with pairs like this, and the coefficients are all 0 or 1, so in this case, all problems have been resolved. And there is a unique, nice solution here. And again, for dimension 2 BI arbitrary, the coefficients arbitrary, there are several competing solutions for how to deal with the moduli problem. But again, all these problems have been resolved, I believe. And well, that's it. So this is where it currently stops. And the main obstacle to higher dimensions is, again, this boundedness question. So for dimension 3 and higher, this is completely unknown. Even without boundary, yes. And so, and although the rest of the theory can be done, so the boundedness is missing. So all of it is still a theoretical track and theoretical approach, some theoretical results. And for a theory to be, a true theory, one must have preferably a long list of examples. And to even begin with all the applications of MGN bar, such as the Gromov-Witten invariants. So what one must have is something more than just pure theory, which is maybe even explicit, but not computable. And so what the parallel track to this is what I will call the practical track. So the practical track. And so what we have here, what I would like to list is a list of concrete moduli spaces of stable surfaces. Surfaces or surface pairs. And so for a while, this was a very short list. And now it's getting longer and longer and longer. And the pace is quickening. So let me give you this list right now. But I must finally say what the surface pair is, so you understand what's on this list. So a stable surface pair is a pair like this. Where X is a projective, connected, reduced surface. BI are divisors, Bell divisors on X. And these small BIs are some coefficients between 0 and 1. So something that looks like this. And it should satisfy two conditions again on singularities and numerical. And for the singularities, I will be brief here. So I will just say that the singularities are of a certain class, which are called semi-log canonical. And I'll leave the explanation for later. And the numerical looks very similar to what we had before. And it just says that K plus B is ample. And so with this, let me give you this list of everything that's known to me currently. So for these moduli spaces, there is a basic dichotomy, two dichotomies. There is a case when when k plus b is small, and small means almost 0, and the case when k plus b is large, without this restriction, and this case is much easier. And then one can also split all these cases into the cases when b is not 0 and when b is 0. And this case turns out to be much easier. So the hardest of all are the surfaces when without any divisor b. So the first two cases that were computed which allow an explicit description are the cases with k plus b small, and these are. Let me begin with the second one. It's pairs like this, where x is an abelian torsor. So this is the same as an abelian variety without fixing the origin. And B is an ample divisor. And so on an abelian variety, the canonical class is 0. And so therefore, well, k plus b in this case is, well, just epsilon b. The first case, which is a precursor to this, is pairs like this, where x is a toric variety, and delta is the complement of the torus, and b is an ample divisor not containing any orbits. And in this case, again, this part is 0. And so k plus b is very small. And so that appeared in a paper of mine from 02. Another case, the chronology here is, maybe this is really 1 instead of 3. So is an example given by hacking. So the years where those things were published and when they appeared as preprints differ by a few years. So hacking looked at the case of the pairs where you start with a P2 and take a curve of degree d, so degree d curve, and you consider it with the coefficient 3 over d plus epsilon. And then again, kp2 is minus 3. So this is, so k plus b is very small. And so he described the moduli spaces in this case quite thoroughly. Okay, so the for the rest of the list, the k plus b is large. And maybe I'll continue here. The next case that one can immediately try would be some surfaces which are obtained from curves. And one thing you can do is you can look at a product of two curves, and then two smooth curves of genus G1 and G2. And when you degenerate them, well, you can just degenerate them to a product of two stable curves. Or one can look at the symmetric square of a curve. So that's a surface. Or one can look at the curves which are isogenous to a product of two curves. So where there is G is a finite group acting on C1 and on C2, and so acting on the product in such a way that the action here is, say, free action. And so these cases were considered by Van Opstal. In 03 and 04. So he showed, for example, that here, just to give an example, if this genus G1 is not G2, and you degenerate the surface like this, and it degenerates into a product of two stable curves, then this surface that you get in the limit, the deformations of it are again of this form, of the product form. So the modular spaces one obtains this way are quite simple. There are just products of moduli spaces for curves, or a moduli space just for this curve itself. And it's a little trickier in the isogeny case. Okay, case number 7 is a fairly non-trivial case. And so this was done by hacking Heel and Tevelev in 06. And here one considers compactifications, moduli spaces of pairs like this, and there are degenerations where the variety is a projective space and BI are hyperplanes. And that's in all dimensions. Oh, and I'm sorry. So an important part about this is that they did it in this case. Case number 8 is the case of Delpezzo surface X, and the divisors BI, where BI are the -1 curves. So this was done again by those three authors in 2007, and they could only do it when the degree of this Delpezzo surface is 3 or larger. Number 9 is a variation of this. Where VIs are still the hyperplanes, and the coefficients are now arbitrary instead of just being 1. And so that's the case that I did last year. And so from this point on, the list starts growing very, very fast. And so let me give you the rest of it. The next case computed was the case of Campidelli surfaces. And these are surfaces of general type. So here B is 0. So this is this hardest case. And K squared is 2. And PG and Q are 0. So there are many Campidelli surfaces, but one case computed here, this is just one connected component in the moduli of Campidelli surfaces. And 11 is something I will call the uniform covers. And 12 through 15, so I'm not trying to cheat here, but so there are 4 connected components here that were computed. They're called the Bournier surfaces. And again, these are surfaces of general type, and K squared, there are several cases here. K squared could be 6, 5, or 4, and PG and Q are 0. So I remind you that PG is H0 of Kx, which is H2 of O, and Q is H1 of O. So 4 cases of this form. And so all of these were computed this year in a paper by myself with Pardini. And then to this list, I'm going to add two more irregular examples of surfaces. So number 16 is on the list is the theta divisors in principally polarized abelian varieties. And so in particular, if you look at the theta divisors in principally polarized abelian threefolds, then those will be surfaces. So if the dimension of X is 2, then you get some surfaces of general type, and they have k squared equals 6, and PG and Q equals 3. And the last case is the double covers where Y is an abelian surface, and again, I should really say an abelian torsor. It's an abelian surface without the origin fixed. And this is ramified in a divisor which is linearly equivalent to twice the principal polarization.
This is the case k squared equals 6.
Um,
I think. Well, let's do this computation. So if we have A and abelian, a principally polarized abelian variety of dimension 3, and theta is the divisor, then theta cubed will be 3 factorial, which will be 6. And now if you look at the canonical class of theta, of the theta divisor, then that will be Ka plus theta restricted to theta. And so the square of it, so this is theta restricted to theta. So the square of it will be theta cubed as computed in A, so it will be 6. And so for the theta divisors, the canonical square of the canonical divisor is 6. And if we look at the double covers over an abelian,
Any divisor, in a non-singular divisor in an abelian threefold, k squared equals 6 chi. Welcome you have chi equals 1. So that's automatic. I mean, of course your calculation.
Yeah, I hope so. So if we now look at the covers, the double covers of the principal polarized abelian surfaces ramified in 2 theta in something linearly equivalent to 2 theta, then here k squared will be 4, and PG and Q are 2. And so this is the complete list of what's known to me. And if you will notice that's by now, that's a pretty, oh yeah. So this 16 and 17, so I'll put VA 09 to appear for these 2 cases. So as you all notice, this is a fairly long list by now. And so in contrast to that theoretical path, this is some very practical information. And say again?
Are these 3 examples closely related with the example table?
Right. So let me make a little diagram of of how all of these related, and it will be a directed graph. And so that's the relation. So this first case is the most basic and the easiest. And so 2 is obtained as a variation of that. And 9 is also obtained as a variation of that. And so from 2, 16 and 17 are deduced. And from 9, those 10 through 11 and 12 through 15 are deduced. So that's schematically, that's how it works. Vertices. And so this gives a strong combinatorial flavor to all of these branches. And so the description of all these moduli spaces, then they share some common roots, and the description, there are many things in the description which look similar. Now, so all of these cases are fairly recent. They're all this year. And so that's what really gives me an opportunity gives me a reason to talk about this again. These 8 new cases. So what I will try to do after the break, I will try to describe some of them, as easily as I can, to show you how explicit and how basically simple this is. So that's the plan for the second part.